So we ended up on this slide where we're seeing the red lines are the lines of a protostar becoming a star. Important thing to remember. What's the key difference between a protostar and a star?
A protostar is the star spread.
A protostar is what?
Like the star spread, like the very start.
Beginning stage.
Yeah.
I'm sure it's my hearing. I just didn't make out any of the words.
The protostar is like its beginning stages, it's the star spread.
Okay, it's the beginning stages. What has not happened yet?
Has it started producing hydrogen?
Not producing hydrogen. It hasn't started fusing hydrogen in the core. Right, that's the key difference. The protostar is having mass falling in, getting hotter and hotter in the core and higher pressure in the core. And then when it reaches a high enough temperature and pressure in the core for fusion to begin in the core, that's when it goes from being a protostar to a star. And when that occurs, it blows off a lot of its exterior gases so that you can actually see the star after that. Before that, it's mostly enshrouded by gases that were coming in. And a very important thing to note on this is the short life or time for birth, half a million. For a half solar mass star, it takes a very long time to be born, more than 10 million years. For a low mass star, a 15 solar mass star, it's well less than 1 million years for it to be born. So every single thing goes faster with bigger stars, just because it has so much more gravity pulling in that it creates higher temperatures in the core and it has to fuse more mass. So theoretically, a star has to have at least 0.08 solar masses. If you don't have 0.08 solar masses, there isn't enough mass for fusion to be sustained in the core. And so things that have mass less than 0.08 sometimes are given a star classification called brown dwarfs. So you see from 0.016 to 0.08 solar masses, those are brown dwarfs. They're really failed stars. They never got enough mass to become actual stars. And so they're essentially like big planets. You know, they're big lumps out there. They're giving off energy because there was, a little bit of fusion, a whole lot of energy from the material falling in, but they're not stars. So brown dwarfs are that low level. 150 solar masses is an upper level for mass. It's kind of surprising that you would have an upper level for mass for a star, right? You'd think, well, more mass, the merrier, right? It just all comes together. But as you can see here, they heat the surrounding gas so high in temperature that the gas expands out and can't be pulled in if it's that high a mass. So you have these practical limits on the sizes of stars. Our first question, what is the minimum mass of a star? Just blurt it out. Yeah, this is the minimum mass, 0.08. I guess there was 0.8 there as well. That was not the right answer. Yeah. So 0.08 solar masses is the minimum mass for a star. What was this 0.016 solar masses? These here are the brown dwarfs, which technically aren't stars. They're failed stars. I say technically aren't. I'm sure there are people out there who say, oh, yes, they are. Yeah.
It wouldn't be like the 0.16 instead of 0.016?
No. 0.016 is less than 0.08. 0.16 is bigger than 0.08.
I thought the minimum mass was like
This here, the one that's circled, is the minimum mass for a star. So the brown dwarfs are masses lower than the minimum mass. Okay. This here, I've talked about that lots and lots. Let's just go right past that. How is energy produced in the core of our sun? Being specific now to our sun, and that picture is not specific to our sun, by the way.
How is energy produced from our sun?
Yeah.
Isn't it the hydrogen?
Yeah. It's the hydrogen chain. You have hydrogen fusion to produce helium. And it occurs basically by hydrogens colliding with hydrogens. When you have stars that have more mass, they'll reach a higher temperature in the core. And because of that higher temperature, they have enough energy to make an alternative fusion pathway go. And this alternative fusion pathway is a more efficient pathway. It releases more energy. And that alternative method is called the CNO cycle, the carbon, nitrogen, oxygen cycle. And how this occurs is you have a carbon atom, and a hydrogen atom bangs into that carbon atom and gets absorbed. And it creates a nitrogen 13. So let me zoom in because I couldn't read these, maybe you can. But you have the hydrogen coming in and hitting the carbon 12 because it has 12 things in the nucleus, 6 protons and 6 neutrons. You add a proton, just a second, I'll answer. You add a proton and now you have 7 protons and 6 neutrons. What was your question?
So I know this. Does this count as one of our makeup ones though, since technically we weren't able to take it, the test, but
no, remember the makeup ones are only after you have the test completed.
So we don't get a makeup one?
If you come and take the test, remember, like I was telling, I know I was talking to Daniel about this, and I think I mentioned to everyone, if it's a clear night, just give me a call. I'll go out with you. We can get it taken care of. And if you can get that before next lab, the next lab can be a makeup lab. Right? But you have to have this, the whole makeup thing is you get the STAR quiz done, and then you have the incentives to get the STAR quiz done early. Yes.
Does it call you? Do you mean actually call you or like shoot you an email?
Either way.
Do you have your number listed?
Probably not. I'll just give you my actual cell phone number. I usually give people, I've got a California number that I use for Google Voice. It's 402, because they made me change. That's my phone number. Don't call me now, I'm teaching. Fact is, I always have the ringer off, which means that I'm not as likely to pick up as you would hope. And you can call or send a text. Getting back to the topic. So the first step in the CNO cycle is a carbon absorbs a proton, a hydrogen nucleus, and becomes a nitrogen 13. But that nitrogen 13 is not a stable nucleus. It spontaneously breaks into a carbon 13, which is stable. Notice it gives off a positron and a neutrino, 2 things that we saw in that proton-proton chain. The positron and neutrino are part of the process of having the particle interaction that destroys a proton and creates a neutron. So that's why we have those same 2 products that occurred when we had a proton and proton come together, and instead of making a helium with no neutrons, it made a hydrogen 2 and had those. So then you have that carbon 13. So now we had 6 protons plus 7 neutrons because it did that conversion. And then you add a hydrogen, and that gives you the very stable 7 protons and 7 neutrons, nitrogen 14. So the right side of this figure went from the most common and stable isotope of carbon, the carbon 12, to the most stable and common isotope of nitrogen, nitrogen 14. Well, then we just continue on. You have another hydrogen hits that, and so you make oxygen 15, so that would be 8 protons plus 7 neutrons. Once again, that's not stable. You have the particle interaction that destroys the proton and creates a neutron, giving off again the positron and the neutrino. And then you have a nitrogen 15 that's more stable. That is 7 protons plus 8 neutrons. Hit it with a hydrogen, and then the surprising thing happens. Instead of making after nitrogen would be oxygen, well, you do for a moment make it oxygen, but that oxygen is going to be broken off into a helium-4 and a carbon. And so that's the end of the process. You came back to carbon again. So you don't have to have lots of carbon to make this happen, because the cycle will just go around. You start with the carbon, you end with the carbon, and it can continue. So this is an alternative pathway to the proton-proton chain, but it is a little more efficient. It gives off a little more energy, and that's what happens when you have temperatures that are above 20 million kelvins in the core. So that's 4 to 5 million kelvins higher than temperature in the core of our sun. So we believe, now of course, what do we believe? We believe that the core of our sun is about 15 to 16 million kelvins based on computer models, and thus that it can only operate with the proton-proton chain. We obviously can't go in there to explore it. So this is, as we should say, theoretical. We can't go in and make direct measurements, but we can look at the neutrinos and count the number of neutrinos. This here has a total of 2 neutrinos per the total fusion event. And I believe there were 4 neutrinos for the fusion cycle in the proton-proton chain. Is that right? Does anybody remember? No? I think it was 4, but I could be wrong. But that would be one way to test, how many neutrinos we get by our measurements we make on neutrinos on Earth. Just to make sure we're all on the same page, what is a neutrino? Yep. Neutrino, its name tells you all you need to know. The neut part means it's neutral, has no charge. And the ino is just a diminutive suffix, meaning that it's small. So it's a small particle with no charge. All right, now looking at the internal structure of stars. And of course, this has a lot to do with computer modeling again, but you notice something really weird about these pictures. So let's start with the big star. Does it have convection? Does it have cycles going like this? Yes. Where are they? They're near the core. So you have a convection zone. I'm not going to finish writing zone. You have a convection zone there in the center for a really massive star. Here's a star like our sun. Where's the convection zone for the star like our sun? It's on the outside. So a star, got to change colors. That one doesn't contrast at all. For a star like our sun, the convection is on the outside. And then if you get to this tiny star, one that's about 0.1 solar mass, is a tenth the mass of our sun, just above the minimum, where's the convection zone? The entire thing. Now, it's a lot easier to make measurements of our sun than any other stars to try to verify this, but the computer models suggest that you have complete convective mixing in small stars. Now, this has an important outcome. You have fusion going on in the core with hydrogen fusing into helium. And we talked about the death of our sun, and we said that at the end, the core is going to run low on hydrogen. And so then the core is going to have fusion slow down, it'll collapse, and you have a shell of hydrogen fusion that goes out. But if you have complete convective mixing like you have in these smallest stars, then when the core runs out of hydrogen, what does that say about the rest of the star? It's also out. And so these small stars, when the core runs out of hydrogen, the whole darn star is out of hydrogen. Hence, no shell of fusion going out. Now, I should say, out of hydrogen doesn't mean there's no hydrogen. It's still probably the dominant element, but you don't have a high enough ratio of hydrogen to helium for the fusion to occur. And so when that happens, all you've made is helium, and you have nothing more, no more hydrogen that can fuse. So it just collapses down, never reaches a high enough temperature pressure to cause the triple alpha process. and you have a white dwarf. Was there a giant stage? No giant stage. So it just kind of collapses and forms a white dwarf. And what kind of elements would you have for a white dwarf from a tiny star like that?
Just when helium and hydrogen.
Just helium and hydrogen. So you would have a helium white dwarf there. Our sun will fuse helium to form carbon, so we should have a carbon white dwarf. So there's different types of white dwarfs. And some white dwarfs will have more oxygen in them as well. With the massive star, it can fuse because it has convective mixing in there, but it'll still have shells that go out, so it will still have the same type of death stages. Okay, moving on. Everything here we've talked about many times, right? I told you at the beginning of last lecture, I spent 20 minutes on the first slide, and then I was going to go quick through a lot of stuff because I already mentioned it. The lifetimes on the main sequence. I've already told you that based on calculations, our sun, which is this one right here, should have about a 10 to the 10th, that's 10 billion year lifetime. So during its lifetime, it started on the main sequence here, and it's going to end there. And it'll take about 10 billion years to get there. Yes?
So theoretically, could life on Earth survive a little bit after the sun left the main sequence? If it turned into a red giant, would that
no. Let's start with let's let Aldwin start.
We'd be inside the red giant.
We would be inside the red giant. But even before that, if you look here on the HR diagram, as the sun burns through its lifetime, what's happening to the luminosity? It's getting more luminous. The sun over time is going to give off more radiation. Now, this is not anything to do with the global warming thing. That effect is far too stretched out for us in our lifetimes to see any change from that. But the sun will be getting more and more radiation coming off of it. That's what luminous means, more radiation. Hence, it will be getting hotter and hotter on Earth the longer the sun lives. And so when we get out here to its end stages, even before it becomes a red giant, right now we're somewhere like here. Even before the sun becomes a red giant, it will be much hotter on Earth because the sun will be giving off a lot more radiation. But then when it becomes a red giant, it's going to expand, and the Earth will be inside the photosphere, and Lord knows life couldn't survive at that point. That's what Aldwin was saying.
We'd be dead.
Yes, we'd be dead. But actually, we'll all be in heaven. That's my plan. Notice the lifetimes with mass. We learned before that the lifetime for a star can be calculated roughly as the lifetime of our sun divided by mass raised to the 2.5 power. And so this has marked the lifetimes for stars of different masses, and you see that a star with a mass that's around, 15 million solar masses has a lifetime. I was marking down here. That was the wrong side. It has a lifetime that's going to be just a little bit longer than 10 million years. 15 solar mass is a little longer than 10 million years. One solar mass, 10 billion years. Obviously, the more mass it is, the much shorter the lifetime. So it took less time for it to form. It's going to take less time for it to live. And then it's going to die with the excitement. Stars down here at this end, the low mass stars, a star that starts down here at minimum of 0.08, its lifetime is going to be in the ballpark of 100 billion years. 100 billion? Yeah, 100 billion. How old do we believe the universe is? 13.8 billion years. So if you have a star with a lifetime of 100 billion years and the universe is 13.8 billion years, how many stars of that size have died? Yeah, according to theory, there should be no low mass stars like down here that have died. Yes, unless something else
So does that mean that
caused their
black hole
demise.
that's at the center of our galaxy is never was a star?
That is correct. The black hole at the center of our galaxy, something in the ballpark of 3 million solar masses, could have never been a star. And we'll talk about galaxy formation, and I don't know, it's probably scheduled for this week, but it ain't going to happen this week. But galaxy formation is essentially the same as star formation. You have a bunch of gas that is gravitationally held together, and of course the gravity is going to pull harder on things that are closer to the center because it's inversely proportional to separation squared. And so you have a lot of mass that got pulled into the center, making a very massive black hole at the center. And that massive black hole is not the result of a supernova. It's just a result of the direct infall of all that mass. Okay, a reminder that the stars have to have their balance between the inward force and the outer force. And stars remain stable in the main sequence for millions, billions of years, but they're not always stable. The thermostat breaks when they're dying. There's also some stars where as they're forming, as they're coming into the main sequence, they go through what we call an instability strip, where they also aren't in equilibrium. When they're not in equilibrium, well, it's just like when you're in a swing. In a swing, equilibrium would mean you're just sitting still. But if somebody pushes you, you swing back and forth, you come through the equilibrium position, but you keep moving. And so you swing back and forth. And that's what the stars do as well. So I guess this wasn't leading me directly to the discussion on the variable stars. This was just talking about the red giant phase. Well, the red giant phase we've talked about enough. Here is now death. Notice we started today's lecture with the birth of stars. We had red lines coming in from the left. Now we have the death of stars. We have red lines leaving the main sequence going to the right. And what's going on, like in this part right here, what's going on there? Is fusion occurring in the star? Notice I said in the star. Yes, fusion's occurring in the star. Where is it occurring? Primarily.
In its shells.
In a shell. So as that shell is burning out, that's making you expand more and more and more. But then this is going to come back down like this. And what makes it come back down?
It got stable again.
It gets stable again because you have more fusion starting up in the core. What's the fusion going to be if you're out of hydrogen? Helium. Through the triple alpha process where the 3 helium all come together at the same time. And you'll notice that no matter what the mass is, you have, trying to draw there the curve on where it begins, that upward going into the giant stage. Now, of course, it's the radius is getting larger as you go that direction. So these started big and are getting bigger and bigger and bigger, but here's where you have that shell burning up. So let's talk about the helium fusion, the triple alpha process. Remember, I told you you'll see pictures that show, 2 helium coming together. But this thing here, that is unstable. That thing doesn't hang around. So as soon as you make that, you have to have the next collision. Otherwise, it's just going to break back apart. So I prefer to think of this picture as taking out the portion that I put the circle around and just having this come up and hit right there and produce the carbon. Because the time has to be so short between all 3 of the helium coming together. But that's what the triple alpha process is. Because you have to have 3 come together in very short time, that means you're going to have a really high pressure. Because pressure is telling us about how frequent collisions are. The higher the pressure, the more frequent the collisions are going to be. You also have to have a very high temperature because, well, what keeps protons from colliding with each other? It's what? Actually, the strong force is what holds them together once they collide.
The weak.
Not the weight. The weight would actually be attractive, but it's a really small force compared to the strong force.
Electromagnetic.
It's the electromagnetic force. Positive charge of a helium nucleus, positive charge, or hydrogen, I said. Positive charge of hydrogen nucleus, i.e. a proton. Positive charge of hydrogen nucleus. When they come together, there's a force that pushes them apart, so they usually come apart and they don't touch. That's why you have to have high temperatures like, 10 million kelvins or so to make them actually come in and touch. I said 10 million, just made that up off the top of my head. It might be 1 million problem. So you have to have high temperature to make hydrogen fusion occur. Helium fusion, instead of having one proton, you have 2 protons in each. So that means you have double the charge in each one, which means that the actual force that's pushing them apart is 4 times bigger, which means the temperature is going to have to be much higher to make the hydrogen fusion occur. So for hydrogen fusion to occur via this triple alpha process, it has to be like 100 million kelvins. That core is stinking hot to make the hydrogen fusion occur. So it's got to be a pretty big star to be able to, develop that kind of temperature. Okay, hey, look, I was pretty much right. 10 million kelvins is what you need. 10 million kelvins is what you need to make the hydrogen fusion occur. So 10 million kelvins for hydrogen fusion, 100 million kelvins for helium fusion. And that's all I need to say about that. Yeah, we can. This here is focusing now on the stable helium fusion is inside of that ring. The helium fusion started up here when it started coming down, but the stability was reached when it got into that white. I called it a ring, oval. I've already mentioned the electron degeneracy, and so I'll just stay real short on this. Quantum mechanics says that you can't pack electrons too close together. If you do, as you try to put more pressure, instead of them actually packing more, their energies just go up. And so we call it a degenerate gas when you have it packed as tight as you can. Now, I said that you put more pressure and it doesn't really do anything. If you add more mass, you'll actually make the volume that it takes compress a little bit. And so when you get up to a mass of 1.4 solar masses, you actually have a high enough force to crush the electron degeneracy and make them come together. So 1.4 solar masses is the maximum mass that can be held up by electron degeneracy. So when we talk about a white dwarfs have an upper mass limit of 1.4 solar masses, because if you get above 1.4 solar masses, you'll crush that electron degeneracy. So there's a name for this 1.4 solar mass limit. It's called the Chandrasekhar, I don't know. Seth tried to teach me to say it right last year. It's called the Chandrasekhar limit. The maximum mass you can have for a white dwarf. So one of the things we're going to learn about real soon is a nova. A nova actually occurs when you have a white dwarf that is gaining mass. How could a white dwarf gain mass? How can a star gain mass?
It got close to it.
It's got to have a companion that is giving it mass. And so you can only have a nova if you have 2 stars together, a binary system. And one star has already died and become a white dwarf, and the other one now gets into its red giant state, so it's blowing off copious amounts of mass. The little white dwarf says, "Come hither." And so it gets mass from its companion that's dying, and when it gets enough mass on its surface, the surface, remember, super hot white dwarfs, so that surface is so hot, you get enough mass, you get enough pressure on the surface, that you have hydrogen fusion occur on the surface. And when the hydrogen fusion occurs, the entire surface exterior of the white dwarf erupts, the interior shrugs, and then you had that fusion of hydrogen to helium, so you just have more helium after that. So it's slowly building up, going through a nova and making it to helium. And as the mass gets larger, if it gets up to 1.4 solar masses, then it will just crush everything and explode and leave nothing behind except for a big cloud. So that's what a nova is. Helium flash is a really interesting thing that goes on. We talked about electron degeneracy. With the helium flash, you have, of course, the core is primarily helium after you've fused hydrogen to helium. And so the core stops fusion of hydrogen because it's run out. You have a shell burning outward, and so the pressure and temperature in the core just starts building up. And if you have a mass that a star with a with a low mass, like less than half a solar mass, it will not get to the degeneracy. Actually, do I have that right? Basically, degenerate before it grows hot enough. Okay. I didn't think about the low mass limit. I was just thinking about the upper mass limit. I think the upper mass limit is about 3 solar masses. I suddenly hit something that I wasn't prepared for. The low mass stars actually reach, as this says, reach degeneracy before the hydrogen fusion has ended, because it's running low on material. It's getting higher temperatures and pressures to keep the fusion going, and it gets to that degenerate point. Higher mass stars, the core won't be degenerate until after. Degenerate means that it's being held up by the electron degeneracy. It doesn't mean anything like, that person is a degenerate human. It's just saying that it's held up by what we call electron degeneracy by this quantum physics thing. So the higher mass stars, after it's finished fusing hydrogen, it'll have this helium core, and the pressure gets higher until you have that degeneracy holding up the helium core. And when that occurs, you have kind of the same idea as what occurs with superheating a fluid. Did you know that you can heat water above the boiling temperature and not have boiling occur? Russell did.
Yeah, I know that because the guy burned himself in this.
Yes. If you've ever heard about people who put water in a coffee mug and stick it in the microwave and leave it on for 10 minutes instead of 1 minute, and then they take it out, and when they take it out, all of a sudden it just explodes and they get very badly burned. You ever heard stories like that?
Yeah.
They really do occur, and it's because you can actually heat the water above its boiling temperature without boiling occurring. You have to have something to start the boiling. And if you have a nice smooth mug with no scratches or anything, you have nothing to start the boiling, and it won't start boiling until something bumps it. And when something bumps it, like you pulling it out, all of a sudden that starts the boiling, and it's all over the temperature, the boiling temperature, and it all boils at once. Hence the explosion. Right? It's not a boom explosion, it's just everything goes from liquid to gas really quickly, and you get scalded. So how do you stop that from happening? Well, number one is don't make a mistake. What?
Put something else in there.
Yeah, you can put something else in there. If you take chemistry class, Russell is a chemistry major, you just put a rock in there. You call it a boiling chip. You put a rock in there, and that rock has its rough surfaces, and it's going to make sure that it doesn't get overheated. Or if you have an old mug that you've scratched up, the scratches will serve to protect you. So, there are ways to avoid it, but that's...
You just put it on 1 minute.
Yeah, another option is just put it on for 1 minute. That also helps. I'm sure you've heard stories about people in dormitories who accidentally put popcorn in for an hour instead of a minute.
I knew a guy who put an egg in the microwave. That was interesting.
In the shell? Yeah, that wasn't wise.
Actually, no, it wasn't in the shell, but it was hard boiled.
Nothing wrong with hard boiled then. It's not going to explode. Okay, but let's stick with this. If you have the core of the star degenerate, when it finally reaches the conditions for helium fusion to begin, the entire core will start helium fusion all at once. So it's the same idea as having that overheated water that all boils at once. And so when you get to this situation, when helium fusion occurs, the entire core essentially starts going crazy with a big explosion. And so that's called the helium flash, the words I underlined. Of course, once the helium fusion starts, it pushes things out a little bit, lowers the pressure so that it becomes non-degenerate, and so it will just have a very quick explosion, and then it will fuse in a more stable fashion. And so if you have a star that's more than a half a solar mass, less than about, I think it's about 3 solar masses, you'll have that helium flash occur when fusion begins. Now the variable stars. This is an actual picture of a variable star. I think it's for Algol, but I'm not positive. There's lots of variables. But if you look, this star, same star I put a box around. Not the same looking though. Algol is a fairly famous variable star. It's the eye of the Medusa. Perseus is holding the head of Medusa and has this eye. Of course, if you look at the eye, it'll turn you to stone, right? Hence the meme about Medusa objectifying people. Yeah. I read it and thought it was just a little funny, so I had to share it. So stars, some stars will get brighter and dimmer, and Algol gets brighter and dimmer with a period of about 1.8 days. What that basically means, if you go out one night and Algol is bright, if you go out the next night, it's probably going to be dim, which is pretty cool. You know, I mean, you expect them to be stable. So now what we're going to look at is, how is it possible for a star to get brighter and dimmer? And it's because it's not stable. Here are some light curves looking at the light that comes from different stars. This top one is called an R.R. Leary variable. The AE is the possessive form of Lyra. So that's R.R. Leary is the R.R. brightness. Remember, alpha, beta, gamma, delta counts down the brightness. After you get done with the alphabetic, then you go to, or after you get done with the Greek, then you go to the regular ABC, and then you start doubling up. And so this is somewhere way down the line in brightness in Lyra. But if you look here, you have a very reproducible brightness pattern. And notice the period here. The period is the time between when it's bright and when it's bright again. That's only a quarter of a day for this R.R. Lyra variable. So that is a very rapid fluctuation in brightness. If we look over here at the Mira variable, our sun could become a Mira variable. Its period, I don't know how I changed tools, but that's going from 200 days to, let's say, 500 days. 200, 500, that's 300 days. That's almost a year. That's a very long period for its fluctuations. And then here's a Cepheid variable. If you look at the period for the Cepheid variable, you're talking about 6 days in this picture. So you have different types of variable stars with distinctly different periods. The Mira variable, very long period. The R.R. Leary, very short periods. And the Cepheids, there are actually two types of Cepheids, Cepheid type 1 and type 2, that are intermediate periods. The last picture, of course, it says non-variable. A normal star doesn't vary in luminosity like this. So these are regular variables here. Regular. There's also some irregular type. The novae, I talked about that. The novae are the white dwarfs that are erupting. T Tauri stars, that's named after T, so it came earlier than RR in the sequence, in the Taurus constellation, are actually stars that are unstable as they're being born. So they've started fusion, but they haven't reached equilibrium. They're going like this. So let's look at how this occurs. So first, there's actually a region in the HR diagram that's called the instability strip. And that's the region where you have yellow giants. They're not stable. And the process here is actually really interesting. It's kind of hard to understand. It's hard for me to understand. Since I have a hard time understanding, I expect you to have a hard time too. But what happens is you have a star that will, let's say it's varying and it's in the collapse size. So it's its smallest size. Because it's smaller, it's giving off less light. So that's going to be the dimmer part of its phase. When it's collapsed down, the atmosphere is less transparent. That means it's going to absorb more energy from coming up from below. So it's going to get hotter. Well, what happens when the atmosphere gets hotter? It naturally does what? Gas gets hot, what does it do? It expands. And so that atmosphere then expands because it was absorbing the radiation. It expands, it's got a bigger area, it gives off more light. But when it expands, it becomes more transparent. And so then the radiation goes through instead of being absorbed, it cools back down and it contracts again. So the process, the whole instability, is caused by the atmosphere when it's contracted, absorbing light. When it expands, the light goes through it. And so it contracts, absorbs, expands, lets the light out, and cools. So that's what is causing it. This is just a picture trying to illustrate it. Okay, here's the picture I wanted. I'm going to go back to the previous one. But this picture is showing where the instability strip is. Just to make sure it's clear, that's the instability strip. In that combination of temperature and luminosity, you can have variable stars. Now, the Mira variables are somewhere out here, and our sun, it's going to go something like that. So our sun could be a Mira variable when it's in its dying stage. So stars that are forming, so if I have a star that's forming, that's coming like this, and it's in here, it can be a T Tauri star. And then when I have a star that's dying, and it goes like this, when it comes through here, then it would be one of the other types of variables, either a Cepheid or a Lyra. You see the RR Lyris are down here and the Cepheids are up here. So it depends on where you are, which type it is. So here is a graph showing the period as a function of the luminosity. This was one of the really important things that Harlow Shapley noted that helped him to identify where the center of the Milky Way galaxy is. Notice with those Cepheid variables, there is a pretty linear looking line here. Now, I say linear line. If you notice the vertical axis, 10 to the 2, 10 to the 3, 10 to the 4, that means each of those lines is 10 times bigger than the one above. That's not a linear axis, that's a logarithmic axis. Likewise, for the horizontal, you see the spacings are kind of varying. And if you go from 1 to 10, and then from 10 to 100, those are the same distance. That's also logarithmic. But on this log-log graph, you have what looks like a very straight line for the relationship between the luminosity and period of a Cepheid variable. Now, the RR Lyris are pretty much constant. It doesn't matter what its luminosity is, it's going to have the same period. But with the Cepheid variables, that gives you a unique ability to know what the luminosity of a star is. Because if you can measure its period, like the period's not hard to measure. Hey, it's bright or it's dimmer, it's bright or it's dimmer, let's time it. But it's not hard to measure the period of the variable. So if you measure its period, and you verify that it's the type that's the Cepheid variable, so you look at where it is on the HR diagram to determine that, then you can say, well, based on this, I know its luminosity, and I know then how bright it is, how luminous it is, I can determine its distance. And so that's what Harlow Shapley was doing. He was determining the distances to Cepheid variables. And I mean, we haven't talked about Shapley yet, but we will, and it was using this information. That's the end.